Hello everyone, this is Jesse Crawford with New York Medical College, and this is a lecture on 2x2 contingency tables. This is an example of a contingency table. We have a sample of 300 people, and they're broken down according to whether they're in Group 1 or Group 2, and whether or not they have a certain disease. For example, we might be interested in a certain respiratory disease, and then Group 1 may consist of people who do not smoke, and Group 2 may consist of people who do smoke. The question that we're going to be interested in is whether the prevalence of the disease is different in these two groups. Of course, we can just calculate the percentage of people in each group who have the disease. In this case, 14% of those in Group 1 have the disease, while 23% of those in Group 2 have it. But you got to keep in mind that this is just a sample, and just because there's a difference between the two groups in a sample doesn't mean there is a difference in the population. In this lecture, we'll discuss a statistical test used to determine if there is a statistically significant difference in the prevalence of the disease in the two groups. Before that, we need to cover some of the terminology related to contingency tables. The first question on this slide asks us what proportion of subjects in Group 1 have the disease. In order to calculate this, we just take the number of people in Group 1 with the disease, which is 14, and we divide that by the total number of people in Group 1, which is 100, and we get 0.14. Notice that the notation for this is P1 hat. So P1 hat is the proportion of subjects in Group 1 with the disease, and P2 hat is the proportion of subjects in Group 2 with the disease. And you can see that we've calculated P2 hat in exactly the same way. We've just taken 46 divided by 200 and got 0.23. The next question is, what proportion of subjects have the disease overall? In other words, if we combine both groups together. Looking in the table, we can see that there are 60 total people with the disease, 14 from Group 1 and 46 from Group 2. And there are 300 total people in the entire table, 100 from Group 1 and 200 from Group 2. So we just take 60 divided by 300 and get 0.2. Now that we've calculated the sample proportion for the two groups, we're going to calculate a couple of quantities that involve comparing these two numbers. The first is the risk difference, and you'll see in parentheses it says Group 2 minus Group 1. So to calculate that, we're just going to calculate P2 hat minus P1 hat, which is 0.23 minus 0.14, and the answer is 0.09. This number basically tells us that the probability of having the disease in Group 2 is 9 percentage points higher than the probability of having the disease in Group 1. The second question says, what is the relative risk? And it says Group 2 over Group 1. To calculate relative risk, we're going to just calculate P2 hat over P1 hat, and we're going to just get 0.23 over 0.14, which is 1.64. And this number just says that the chance of having the disease in Group 2 is 1.64 times higher than the chance of having the disease in Group 1. Now I'd like to talk about something that we discussed at the beginning of the lecture, and that's the distinction between sample proportions, population proportions, and a statistical testing problem that's related to these. Now we've already calculated the sample proportions. We found out that the proportion of people with the disease in Group 1 was 0.14, and the proportion of people with the disease in Group 2 is 0.23. But these are just the sample proportions. What we actually care about are the population proportions. So to go back to an example from earlier, if the disease in question is some kind of a respiratory disease, and if Group 1 represents non-smokers and Group 2 represents smokers, then what we really care about is what proportion of non-smokers in the population have the disease, what proportion of smokers in the population have the disease, and is there a difference between those two proportions? The problem is that we don't actually know what the population proportions are, because in order to determine those, we would have to talk to every single non-smoker and every single smoker and figure out for each person if they have the respiratory disease or not, and that would take way too long to do, and it would probably be prohibitively expensive also. So what we really need is some kind of a statistical test that uses the sample data and determines if there's a statistically significant difference between the sample proportions, which should provide us some evidence of whether or not there's a difference between the population proportions. One last thing I'll mention is, notice that there's a notational difference here. The sample proportions are represented by P1 hat and P2 hat, and the population proportions are P1 and P2. And so again, what we really care about is, are the population proportions the same, or are those different? So in other words, we care about, is P1 equal to P2, or is P1 not equal to P2? And this is a very good example of a statistical testing problem. Our null hypothesis is going to be that there's no difference between the two groups, which would say P1 is equal to P2. And our null hypothesis is represented by H sub 0, or what usually people call H naught. And then our alternative hypothesis says there is a difference, in other words, P1 is not equal to P2, and the alternative hypothesis is usually represented by H sub A. And so to state the hypothesis in one simple statement, you can just say H naught P1 equals P2 versus HA P1 not equal to P2. Now that we've talked about this hypothesis testing problem, I'd like to go back to the concept of relative risk that we discussed earlier. So remember this question, it said, what is the relative risk, group 2 over group 1, and we just took P2 hat divided by P1 hat, and we got 1.64. Well, the question under that is saying, what is the relative risk in the population under the null hypothesis? Well, to answer this question, we simply have to think back to what the null hypothesis says. The null hypothesis says that the population proportion for group 1 is equal to the population proportion for group 2. In other words, P1 is equal to P2. Well, what about the relative risk in the population? The relative risk in the population is equal to P2 divided by P1. But if P1 is equal to P2, then P2 divided by P1 is just going to be equal to 1. So this is a pretty interesting question. It shows us that if the null hypothesis is true, then the relative risk in the population is equal to 1. Alright, one last bit of terminology that we need to talk about is the concept of odds. The first question says, what are the odds of having the disease in group 1? In order to calculate odds, you just take the number of people with the disease and divide by the number of people without the disease. So for group 1, we're going to take 14 divided by 86, and we're going to get 0.163. We do the same thing in group 2, 46 over 154 is 0.299. And then the third question says, what is the odds ratio? And that's exactly what it sounds like. It's just the ratio of the two odds. So you just take the odds for group 2, divide it by the odds for group 1, and we get 1.83. This question asks us, what is the odds ratio in the population under the null hypothesis? This is pretty similar to a question we just answered about the relative risk in the population under the null hypothesis. Again, we just think back to what the null hypothesis says. It says that the population proportions for the two groups are the same, that P1 is equal to P2. But if the population proportions are the same, then the odds are actually going to be the same also. In other words, O1 is equal to O2. But if you think about what the odds ratio is, it's just equal to O2 divided by O1. And if O1 is equal to O2, then once again, we're just going to get 1 when we do that division. And so the null hypothesis is equivalent to the relative risk being equal to 1, and it's also equivalent to the odds ratio being equal to 1. Okay, we're pretty much done discussing all the terminology associated with contingency tables, and we're ready to talk about the statistical testing problem in more detail. So a quick reminder, we're looking at the population proportions P1 and P2, and what we're really interested in is, are these two population proportions the same, or are they different? In other words, we want to test H naught P1 equals P2 versus HA P1 not equal to P2. So we need to develop some kind of a statistical test that looks at our sample data and determines whether there's a statistically significant difference between group 1 and group 2. This test is called the chi-square test, and most of the rest of the lecture will be dedicated to talking about how the chi-square test works. Okay, so let's talk about how this chi-square test works. You'll notice on this first slide that we have two tables. The top table is the table that we've been looking at throughout the entire lecture, and the title of that table is Observed Frequencies. Keep in mind that frequency just means the number of subjects in a certain group, so when we say observed frequency, we just mean the observed number of people that are in each of the groups that we're talking about here. So for example, there's 14 people in group 1 with the disease, so the observed frequency in group 1 with the disease is 14. So the idea of the chi-square test is we're going to build a second table called expected frequencies. And these are the frequencies that we would have expected to occur if there was no difference between group 1 and group 2. And there's a simple formula we're going to use to calculate these expected frequencies. It's expected frequency equals row total times column total divided by table total. Okay, so let's use this formula to get the upper left corner of the expected frequencies table. In order to do this, we need to look in the upper left corner of our original table that has a 14 in it, and we're going to be using the formula row total times column total over table total. Well, for the cell that has a 14 in it, the row total for that cell was 100, and the column total corresponding to that cell was 60. So we just do 100 times 60 divided by the table total, which is 300, and that gives us 20. So 20 is what we're going to put in the upper left corner of the expected frequencies table. Now we're ready to calculate the upper right-hand corner of the expected frequencies table. So we just look in the upper right corner of the observed frequencies table that has an 86 in it. The row total is 100, the column total is 240. So we just do 100 times 240 over 300 and we get 80. 80 is going to be the number that we put in the upper right-hand corner of the expected frequencies table. One thing that's kind of interesting is we don't actually even have to do this calculation because the row total in the expected frequencies table has to be 100. And so since there was a 20 in the upper left corner, there has to be an 80 in the upper right corner for those two numbers to add up to 100. So actually, once you get the upper left-hand corner, you're going to be able to get the entire rest of the table by just doing simple arithmetic. Okay, this is our third example of applying this formula to find the bottom left cell in the expected frequencies table. If we look in the bottom left cell of the observed frequencies where the 46 is, we have a row total of 200, column total of 60. Plug those numbers into the table, we get 40, and so that tells us that the bottom left cell in the expected frequencies table is 40. But again, we could have just used the column total to do this. We see that the disease column has a total of 60, and since the upper left cell has 20 in it, the lower left cell has to have a 40 in order for those two to add up to 60. Here's our last example where we're going to calculate the bottom right corner of the expected frequencies table. There's a few different ways we can get this number. We could just use the formula, in which case we get 160, or you can just use the row total. The row total's 200 and we've got a 40 in the bottom left corner, so the bottom right has to be 160. Or you could even use the column total. The column total's 240 and we've got an 80 in the upper right, so this bottom right has to be 160. Okay, now that we've calculated all these expected frequencies, what are we going to do with them? Well, we're going to combine them with our original observed frequencies in order to calculate something called Pearson's chi-square statistic. And the formula for the chi-square statistic is given below. It says, calculate the summation of OI minus EI squared over EI. In other words, for every single cell, you're going to take the observed frequency, subtract the corresponding expected frequency, and square that number. Then you're going to take that number and divide it by the expected frequency. And finally, you're going to do that for every single cell and add all those numbers together. So for example, for our upper left cell, the observed is 14 and the expected is 20. So we're just going to do 14 minus 20 squared over 20. For the upper right, observed is 86 and expected is 80. So we have 86 minus 80 squared over 80. Then for the lower left, we'll have 46 minus 40 squared over 40. And finally, for the lower right, we'll have 154 minus 160 squared over 160. And if you do all these calculations and add them up, you get 3.375. So the Pearson chi-square statistic for this problem is 3.375, and the next slides will show how to interpret this number. Keep in mind that the expected frequencies are the frequencies that we would have expected if the null hypothesis were true. The observed frequencies are the ones that we actually observed. So if there's a big difference between what we observed and what we would have expected under the null hypothesis, then the null hypothesis is probably not true. So if we see big differences between observed and expected, that's evidence against the null hypothesis. Now if we look at the chi-square statistic, that's really what it's measuring. It's calculating observed minus expected. That's basically the distance between the observed and expected values. It's squaring all those and adding all those up. So if there's a big difference between the observed frequencies and the expected frequencies, that's going to actually make the chi-square statistic really large. So I hope this kind of helps to understand that if the chi-square statistic is large, that's actually strong evidence against the null hypothesis. And if the chi-square statistic is small, then that's evidence that we should retain the null hypothesis. And the next slide we'll talk about this in more detail. On the previous slide, we talked about how to calculate the chi-square statistic, and we said that if the chi-square statistic is large, then that's evidence against the null hypothesis, and if it's small, that's evidence that supports the null hypothesis. In other words, if the chi-square statistic is large, we're going to reject the null hypothesis, and if it's small, we're going to retain the null hypothesis. And the question is, where's the boundary point? Where's the cutoff value that determines whether we're going to reject or retain the null hypothesis? The chi-square statistic has a chi-square distribution, and the chi-square distribution is kind of like the t-distribution. It has a degrees of freedom associated to it. Now, generally speaking, you could look at a contingency table that's bigger than a 2 by 2 table. It might have a bunch of rows and a bunch of columns. And the degrees of freedom for the chi-square distribution is equal to r minus 1 times c minus 1, where r is the number of rows and c is the number of columns. Now we're just dealing with the 2 by 2 table because we just have group 1, group 2, and disease or non-disease. So that's really just a 2 by 2 table. And since it's a 2 by 2 table, if you plug 2 in for r and 2 in for c, you just get 1 times 1, which is 1. So long story short, if you have a 2 by 2 contingency table, the chi-square statistic is just going to have a chi-square distribution with 1 degree of freedom. That means if you want to figure out whether or not to reject the null hypothesis, we need to look at a statistical table for a chi-square distribution with 1 degree of freedom. And you see a table like that on this slide. So for example, if we have an alpha level of 0.2, then the cutoff value corresponding to that is 1.64. Since we got a chi-square statistic on the previous slide of 3.375, 3.375 is bigger than 1.64, so we would actually reject H naught at the alpha equals 0.2 significance level. On the other hand, if our significance level was 0.05, the cutoff value for that is 3.84, and since we're not bigger than 3.84, we would retain the null hypothesis at a 0.05 significance level. The chi-square test that we just went over is actually based on an approximation, but it'll work really well as long as the values in your expected frequency table are large. However, if any one of the frequencies in your expected frequencies table is less than 5, you have to use Fisher's exact test. Fisher's exact test is something that will be covered in a more advanced biostatistics course or epidemiology course. This last slide covers concordant and discordant pairs, and the example here is similar to a homework problem where a bunch of couples are asked whether they approve or disapprove of some policy proposal. The couples are broken down according to whether the husband said yes or no or the wife said yes or no. So the first question says how many pairs are concordant. A concordant pair is a pair where the subjects are the same. So we have 30 pairs where the husband and wife both said yes, and we have 25 pairs where the husband and wife both said no. So those are our concordant pairs, so we have 35 plus 25 is 55. Then the second question says how many pairs are discordant. Discordant pairs are the ones where the subjects are different. And so we have 4 pairs where the husband said no, the wife said yes. We have 6 pairs where the husband said yes and the wife said no. Those are the ones where they're different. And so there are 4 plus 6, which is equal to 10 discordant pairs. Okay guys, that wraps up the lecture on 2 by 2 contingency tables. As always, please let me know if you have questions on anything. If you have any questions on the homework or this lecture, please let me know in the homework and lecture help question form, or you can send me a private message.